Good morning. Let's pick up again with chapter 38. So we had spent quite a bit of time in chapter 38 looking at these wave functions for particles confined to a certain region, is what we called that. And so we had derived, using the Schrodinger equation, we had derived what the wave functions would look like mathematically. So here's an expression, a general expression for the possible quantum states that we would have. And the quantum states themselves look like sine functions, whereas the probability densities, the squares, look like sine squared functions. So we said that the wave functions contain all the information about the particle. The sine squared, or the wave function squared, tell us how the probability of finding the particle will vary from one location to the next. So that's what these look like, and we had just carried out an integration, finding out how to normalize these mathematical expressions, and we had carried out an integration and then solved for this factor, normalization constant out front, and shown that to be 2 over L square root. So that was the normalization constant. Now, there's another way of getting this integration. If we take the wave functions, are going to integrate out to be 1. There needs to be a dx right there. Add that dx right in there. So there's a dx right here. This needs to integrate out to be 1. And then we factored out the a squared. What we're left with inside here is a sine squared function integrated over some length, 0 to L. So if we take a sine squared function of anything, sine squared of u, or sine squared of x, or sine squared of whatever's in here, and we integrate it over some number of complete cycles. So the example that I drew over here, let's say that we integrate this thing over 3 complete cycles. Well, the sine squared and the cosine squared are like complementary functions of each other. If we integrate sine squared or cosine over a full cycle, the average value for that function is going to be 1/2. And that says that if I integrate a sine or a cosine, they peak at the value of 1. And if we integrate them over some length L, half of that volume, half the area under the curve, will be the sine squared function. Half the area under the curve will be the cosine squared function. So that's kind of a trick with these sine squared or cosine squared functions. So you don't really have to stop and carry out the integration. You can just, if you can verify that we're integrating over complete cycles, then you can just take 1/2 the length. And that will be the area under the curve. That's kind of a shortcut way of getting at that normalization constant. All right, so now that we've normalized the wave function, what we can do is go in and ask some other questions about probabilities. So what they're saying here is that, once again, they've got an electron in the ground state within this confined region. And it wants to know if we take a very, very short region here. This is 1 picometer, 10 to the minus 12. That is 100 picometers of width. We're going to be looking at just that one small region. It's small enough that we can think of it as being a width of dx, right at the center. So let's try this. So what this looks like is, now this is the wave function, this is the probability function. So this is the sine squared, that's the sine. The width here, L, is 100 picometers, but we want to find out how much probability is in that central 1 picometer. Now, it only contains 1% of the width, but just by looking at it, you can see that it contains, it's going to contain more than its share, more than the average amount of the probability. So let's take a look and see how we would carry that out. Now, here's the wave function itself. And the new thing that we have out front now is instead of just putting a constant big A all the time to represent the wave function normalization constant, now we know what it is. It's 2 over L square root. So I can start with the 2 over L square root out front. There is the sign factor. Now it's the ground state, so n is equal to 1. There it is. N is equal to 1. N is equal to 1. So I just left the n out. And this is sine squared pi x over L. Now, the little piece of probability here in that little narrow band is going to be the wave function squared times dx. The wave function squared is our probability density. So for this, we don't really have to do any kind of integration. It's such a narrow region. The function is varying almost not at all. And that says we can just take this expression and start plugging things in. 2 over 100 picometers was L. Sine squared of this became pi over 2, which is 1. And then the dx is 1 picometers. Now, if we've done this right, the units should cancel out. And so the picometers in the dx cancel the picometers in the L, and I got a probability of 2 over 100, or 0.020. I got 2%. So in that 1% of the region, in terms of width, I've got double the probability on average. And that makes sense. If you look at the sine squared function here, the average value is 1/2. But right in the center, the sine squared would have a value of 1. And so it's going to have twice as much probability as an average. If we picked some other place at random, the one in the middle would have twice the probability of the average of all the others. All right, so probability just at the center. But remember, that's only 1 picometer out of 100. Okay, now they're going to have another probability calculation problem. So they're going to do kind of a series of these and see what we can come up with. Now, in their example, they said, assume the electron is in the ground state. Ooh, what if we don't? What if we assume any one of the quantum states? What if there were a way we could do this for every quantum state all at once? I don't know if it's a good idea, but we're going to try it. But they're really only asking us to do the ground state. So they're looking at the region between one of the walls, one of the infinite potential regions, and 1/4 of the way over. So let's see what this problem looks like. Now, I drew wave functions 1, 2, and 3, and wave function 1 has 1 peak, kind of mostly in the middle, and wave function 2 has 2 peaks, and wave function 3 has 3 peaks. Now, this, we keep looking at these pictures. It's worth stopping and asking what's going on here. And it says that if you had an electron in an atom or a molecule or some other region where it was really strictly confined to that region, the electron would know enough to stay away from the edges. So that's one of the predictions from quantum mechanics, is that even though the electron is free to move about anywhere inside there, it's not equally likely at every location. The probability in the ground state is bunched together in the middle, and it stays away from the edges. It knows how to do that. Apparently electrons know all about quantum mechanics. They have taken differential equations, they know about boundary conditions. When the electron jumps into, say, state number 2, this is even more unusual. in that the electron knows to stay away from the middle region. If it's in quantum state number 2, the electron knows to stay mostly in these regions around 1/4 and 3/4 of the way across, but to avoid the walls and avoid the region in the middle. When we jump into state number 3, the electron knows to avoid these regions at 1/3 and 2/3. Now, this is getting to be a little ridiculous, right? But this is, all the evidence suggests this really works. Quantum mechanics makes very specific predictions as to what the electron arrangements will look like. And when we do experiments to map these out, it turns out quantum mechanics is right. Quantum mechanics correctly predicts what the distribution will look like for these electrons. So anyway, again, maybe I was feeling a little too ambitious when I was solving this problem. Maybe I'd had too much coffee, but I decided that I would go ahead and just solve for all the wave functions. Now, some of these are going to be not too difficult. What they're asking for, and maybe some of them I didn't draw very well, I believe what they asked was between 0 and 1/4 of the way across. Well, for the first quantum state, I've got to go in and integrate that. I have to find the area under the curve. But at the same time, I know a few things about it. I know that it's less than 25%, right? Because if we evenly divided up the probability, it would be 25% in each one of those 4 regions. But this is smaller than average. So that's going to be less than 20. In fact, it could be substantially less than 25%. That's my prediction. It's not numerical yet, but that's the prediction for that. Now, this one here, I drew poorly. I apologize, because if I go 1/4 of the way over on this, that should match up with the peak, right? So I already know the probability for quantum state number 2. Quantum state number 2 is going to have exactly 25% of the probability will be in that first region of 4, because it's symmetric through those 4 regions. So let's see. Quantum state 1 is going to be less than 25%, maybe substantially less. Quantum state 2 is going to be right at 25%. Quantum state 3, now let's look at this one. The node, these are called nodes where they go to 0. The node right there is actually at 1/3, and so this probably on average is more than the average parts of the wave function. I'm going to guess for part 3, it's going to be more than 25%. More than 25% of the probability is going to be in that region. That first third would be 33%. And see, I'm not subtracting very much from that. I'm going to guess that one's going to be bigger than 25, maybe not a lot. So substantially less than 25, equal to 25, maybe a little more than 25. What's state number 4 going to look like? And I'm hoping you guys can visualize this already. State number 4 is going to have 4 lobes, 4 regions of probability, symmetrically placed in these 4 regions that I'm imagining. And that means each one will be right at 25%. In fact, it's starting to seem like all of the even numbered wave functions will be right at 25%, because dividing into fourths an even number of lobes will always give us a symmetric amount. We'll always be able to match up the amounts in each of the 4 regions. So that's a crazy prediction. Let's put that out there. And it's the odd ones that are either going to be, less, or maybe a little more, or maybe a little less than average, than the 25%. So let's try it. Here is an expression that works for every one of the wave functions. For a probability distribution, I've got 2 over L. They all have the same normalization constant out front. And then there's going to be a sine squared of n pi over x over L. And so the probability can be calculated now by going from 0. Now I also put this in as just x. So I kept this pretty general too. Eventually what the problem is asking us to do is to take that x and set it equal to 1/4 L. So eventually we'll do that. We'll set that x equal to 1/4 L, but for now, let's just get a general expression. So I could go across here any amount I want. So we're really solving this much more generally than what the problem asked for. All right, so that gives me 2 over L, 0 to x, sine squared of all that stuff, dx. I'm going to make the same substitutions that we did before. So it's basically setting up the very same integral. The only difference now is instead of integrating over entire cycles, we're going to just integrate over portions of the region. So we can't use our shortcut because it's not integrating over complete cycles, but we can go back and use the 1/2 1 minus cosine 2u. We can use the trig identity to go back and evaluate this integration. So I have my 2 over L, I have my factor of L over n pi, and the L's have already canceled. And so units are gone. There are no more units to be had here. We'll see how that works out. And so what I have out front now is 2 over n pi. I'm still integrating from 0 to x. Now, when I say x, what I really mean is to a u value of n pi x over L. So I'll be substituting that back in at the end. So let's see, this is 1/2 1 minus cosine of 2u du. I think we got everything. And so the 2's canceled. And now I'm at 1 over n pi. The 1 integrates to u. The cosine of 2u integrates to 1/2 sine of 2u. And we're going to evaluate that between 0 and x. Now, this time, instead of putting the u's into the limit, I am going to take these u's in my expression and replace those. I'm going to back substitute into x's. So we substituted into u, did some integration, and now I'm going to back substitute and put the x's and the n pi's back in. So I'm getting p is 1 over n pi x over L minus 1/2 sine, that's a 2, so n 2 pi x over L evaluated between 0 and x. Now, it's still the case at the 0 side, those just become zeros. They drop out. But when x is equal to x, we can substitute that in. For this first expression, that leaves me with x over L. Now, x over L is kind of an interesting term in this probability because x over L is what the probability would be if the function were just flat, right? X over L is the fraction of the way over that we're including. So, for example, in the problem they've given us, x is equal to 1/4 L, and substituting that in, the probability becomes 1/4. Now, that's not the whole story. This next term is going to possibly increase or decrease the probabilities here. So here, I've got 1 over 2 pi times n, the sine of n 2 pi over times x over L. Okay, so both of these are going to have to be evaluated, and let's do it. Let's see what we get for the probability calculation. So here are those three functions again, and I keep drawing them wrong. So I'm a little disappointed with my drawing here. 1/4 should go right through the peak of this one. I think before I drew it on the right side, now I'm drawing it on the left, but it should go right through the peak of quantum state number 2. It's going to pick up very little of quantum state number 1, and it's going to miss. This almost makes it look like 1/3, but the value here is actually 1/4. It's going to come up short. Now, for x equals 1/4 L, the probability reduced down to 1/4 minus 1 over n times 2 pi, the sine of n pi over 2. So with x equal to 1/4 L, the L's canceled out. And I'm left with 1/4 times 2 is pi over 2. And the sine of pi over 2, the sine of n pi over 2 is going to change from one quantum state to the next. So, for example, quantum state number 1, it says the probability will start off as 1/4, but then we have to subtract off 1 over 2 pi. And when I did that, I ended up with 0.091. So this is the one that we said might be substantially less than 25%, and it looks like our prediction was right. So this is only 9% here. Now I could draw another line here and cut off another 9%, and then the middle region would be like 80%, 80 something percent here, not quite, 78%. So, is that right? 18%, 72%. No, 82%. So 82% in the middle region, 41% here, 41% here, 9% here, 9% here. So we can kind of map out how those 4 different regions combine. Now, with the n equals 2 state, which I habitually draw incorrectly, that's going to be 25%, 25%, 25, 25. That one we said we didn't even need to do the integral, but we did. And the integral agreed that it was 1/4. Now, for the third one, this is going to become the sine of 3/2 pi. Now, the sine of 3/2 pi is going to be -1, so that's going to be like switching that minus sign to a plus sign. Now, the n here has gotten bigger. So instead of being 1 over 2 pi, instead of subtracting 1 over 2 pi, we're going to be adding 1 over 6 pi. And when we did that, we got 0.303, about 30%. So a little bit greater than 25. And the pattern is going to continue here, right? So every time we get to an even number quantum state, the probability for that even number quantum state is going to be 25 in that farthest left 1/4 region, because the evens match up in a way where it gets evenly divided. But what's going to happen is 1 was substantially less than 25, 3 was a little bit more, 5 is going to be a little bit less, 7 is going to be a smidge more, because what's going to happen is this factor out front, this is going to keep being 1 or -1. And so that will control whether it's a little bit added on or a little bit subtracted. So it was -1 over 2 pi, now it's plus 1 over 6 pi. The next one's going to be minus 1 over 10 pi. So you can see that it's going to get closer and closer to 1/4. The biggest discrepancies were in these odd quantum states 1 and 3. Anyway, this is how it works. So now that we have a wave function with the normalization constants determined, we can take that wave function, we can integrate it over any region we want, and we can carry out a calculation. So we can either, if we know how to do the integration, we can carry out the integration. If we're not sure how to carry out the integration, it could be programmed, for example. But in any case, we now have methods available to us where you could go in and evaluate the probability for any of these wave functions over any particular region. Okay, so let's move on and take a look at a couple of other questions. So again, we're looking at this particle in a box, infinitely deep, square well potential. I want to say we've spent a lot of time on this. If you look at the practice problem for the midterm, you'll see examples from here for the midterm also. So yeah, this is definitely one of the big topics that we're looking at in this chapter. Definitely something that you want to kind of know inside out, all the properties of these solutions. So what they want us to find out now is what's the most likely value, most likely and average position of the electron. So we're still the electron, it's still a region of 100 picometers. Now it's saying state 2, we can do them all. So it worked out fine last time, right? Instead of just limiting ourselves to the ground state, we solved probabilities for everybody. We got a formula for that. Let's just do this for all possible wave functions. I think we can do them all. Here we go. Here are states n equals 1, 2, 3, 4. Here's what they look like. These are all sine squared functions. Now it said, where are the most likely places to find the electron? And I'm hoping when you guys see these functions, you can just spot the values here. This is x equals 0, this is x equals L. That's x equals 1/2 L, and that's where the function peaks. If there were one point that has the highest probability, it's right in the middle. Now, for quantum state 2, and this we said was weird, but now, instead of having one location, most probable, there's actually 2 locations most probable. And if I look at the numbers here, that is 1/2. That is 1/2 of 1/2. You know what that is? It's 1/4. And that is 1/2 of the way from 1/2 to 4/4. This is 3/4. So we can divide that up into fourths. The peaks are at 1/4 and 3/4. For the n equals 3 quantum state, we can divide that up into sixths. And the peaks are going to happen at the odd sixths. 1/6 is a peak, 2/6 is a node, 3/6 is a peak, 4/6 is a node, 5/6 is a peak, 6/6 is a node. In fact, it's the other wall. So 1/6, 3/6, 5/6. And then for, well, you guys can see the pattern. I drew a fourth one here. I should have done that for the probability so we could see that that was 25% of the probability. But the peaks, the most likely values, are going to be those 4 evenly spaced 1/8, 3/8, 5/8, and 7/8 L's. That's where they would be. Now, that is unusual, that the electron has, you would think, well, why is the electron staying away from these regions? Is it something they said, something they didn't say? But the electrons just know to stay away from certain regions and to be more probable at other locations. Okay, and what does this all trace back to? It traces back to this property of phase and the idea that the energy and the momentum are related to the wavelengths and the frequencies. Okay, specifically in this case, the wavelengths. Which wavelengths are possible to fit in this region? Okay, the other thing that they ask about is what's the average location of the electron? Now, if I averaged out where the electron is located here, I go right in the middle, right? It's just as equally likely to be on the left side as the right side. If I average over all the possible locations, it's going to be right in the middle. Again, I've got ranges of different probabilities, in states number 2, but it's still symmetric. So the average location would still be in the middle, even though the probability of being at that location is 0, right? But when I average everything over this lobe and this lobe, it averages out to 1/2. Same thing with the 3 lobe, n equals 3 quantum state. So every quantum state, the average location is going to be 1/2, even though for many of these states, all the even ones, there's actually no probability of actually being right at the middle. That turns out to be a node. All right, here is our macroscopic example when we were looking at the Heisenberg uncertainty principle. We had an example with a baseball, and now with a particle confined inside a deep square well potential, they've brought out a bacteria. Okay, so a tiny bacterium, mass of about 10 to the minus 14 kilograms, is confined in a 0.1 millimeter region. Now, if you're a bacterium, 0.1 millimeters is a lot of room to move around in. So the 0.1 millimeter, that's not too tiny. Estimate its minimum speed. If instead its speed is about 1 millimeter in 100 seconds, estimate the quantum number of its state. So again, I'm not sure how useful some of these examples are. This is not a high priority question. But who knows, we may learn something if we go in and take a look at it, so why not? Here is the region L, here is the mass. We're imagining that there are going to be quantum states of this bacteria that it could be in, and each one would correspond to different amounts of energy. Now, rather than looking at the quantum states and the energy, we're really going to be bringing back this Heisenberg uncertainty principle or possibility principle. And the idea is, if we want to use a wave function to represent the bacteria and allow the bacteria to be at any possible location, we could say that the delta x then is equal to L. So L, which was, what was L equal to? Here it is, 1 times 10 to the minus 4 meters. So I should have written that down somewhere here. So I've got a delta x. I'm imagining it could be found anywhere. So I want to find out what range of momentum this bacteria might have. Well, if the delta x is limited to 1.0, 10 to the minus 4 meters, that means that the bacterium can't have a fixed momentum of 0. It's got to have at least a little bit of a range of possible values for that momentum. And so we can solve that using the Heisenberg possibility or uncertainty principle. And when I solved for the momentum range, it was 1.055, 10 to the minus 30 Newton seconds. They wanted me to, oh, you know what I did? I did not solve the rest of this problem. Okay, it really is not a high priority problem. But anyway, what it said was the mass is 10 to the minus 14. Okay, so if the mass, this is the momentum. If the mass is 10 to the minus 14, the velocity is going to be like 10 to the minus 16. It's going to be tiny. When we say, even if quantum mechanics applies in this situation, and I'm not sure if it does, even if quantum mechanics applies in this situation, the range of the minimum velocity could be so small it could be essentially considered to be at rest. It would be interesting to find out, though, if bacteria have to have at least a little bit of momentum. They're not allowed to go into 0 momentum. And I just did not do that second problem. Uh-oh, I'm going to lose points there for sure. Okay. not so worried about it. All right, we want to move into a couple of more advanced examples. And first of all, I promised you guys that we would be looking at particles confined to a three-dimensional region and see how three-dimensional regions compare with one-dimensional regions. Certainly the one-dimensional regions, the math is a little more straightforward, but is it a reasonable representation of the pattern of quantum states? So anyway, I drew a three-dimensional region. I kept it as simple as possible. I made it a cube. I made it a cube with sides that are L. I had the potential energy inside set to 0 and the potential energy outside set to infinity. So it really is a particle confined to a region now, and it's three-dimensional, so much more realistic. And the Schrodinger equation then, I can drop off the potential energy. I don't have to include a potential energy term, but my kinetic energy term now needs to include, I can't just write it as px over 2m, I have to write it in terms of px, py, and pz components. I want to include all three. So the px, py, and pz operators are going to be taking derivatives, partial derivatives, with respect to x, y, and z. So now instead of just having one set of partial derivatives, now I'm going to have three doubled up partial derivatives because of the x, y, and the z directions. Now the wave functions that I'm going to use to fit this cubic region, I'll just do x, y, and z as their functional dependence. And we can set one of these corners of the box equal to the origin of a coordinate system. Maybe the one at the back, right there. So we'll have x go off in that direction, we'll have y come over here, and we'll have z coming out towards us. That can be the center of our coordinate system. Now, that says that one side of the box, the box has 6 surfaces, 6 square sides, and one side is defined as the plane x equals 0, and the other is the plane x equals L. And then there is a plane y equals 0 and y equals L, and then there's a plane z equals 0 and z equals L. Now those are surfaces, and the wave function is going to have to go to 0 along those entire surfaces, all 6 of those surfaces. The wave function's got to be 0 right along everywhere on the inside of that cube. Now we can meet all of those requirements. All of the boundary conditions that we just talked about can be set up if we decide to use a wave function that is a product of sine functions in the x, the y, and the z. So kind of the reasoning here is, let's just multiply together a wave function for the x direction times a wave function for the y times a wave function for the z. What that will automatically do for us is it'll keep us away from all the walls. So when x goes to 0, or y goes to 0, or z goes to 0, the wave function goes to 0. Now, to meet the boundary conditions on the other side, I've put in nx times pi, ny times pi, and nz times pi, so that each individual sine function will go to 0 whenever x equals L, or y equals L, or z equals L. So all those boundary conditions, they've all been met by defining quantum numbers nx, ny, and nz. Now, nx and ny and nz individually can be any integer value starting with 1. Again, 0 doesn't work here. 0, the whole wave function just goes to 0 everywhere. So I've got to start off at least nx equals 1, ny equals 1, and nz equals 1. That's going to be the ground state, the lowest energy wave function. Well, let's see if it works. So I'm going to take that wave function right there, this one, and plug it in right there. Now, what I need to do is take a series of second derivatives, second partial derivatives. So let me just see what happens with second partial derivative with respect to x of that wave function. Well, if I take this wave function and the x dependence is only in one place. So I will factor out nx pi over L 2 times because I'm going to take second derivatives. So that's going to leave me with nx squared pi squared over L squared. Now the sine function itself is going to first turn to a cosine and then turn to a negative sine. Again, I'm going to take 2 derivatives, so it's going to give me the sine function right back again, but with a minus sign out front. Now that's going to happen with each portion of the wave function. When I take a second derivative with respect to y, when I take a second derivative with respect to z, the same thing is going to happen. So that says that if I go back to my original Schrodinger equation up here at the top, where I had minus h bar squared over 2m, I now have h bar squared over 2m because the minus sign here is going to cancel with all the minus signs coming out of my second derivatives. When I get to the y dependence, I'm going to have ny squared pi squared over L squared. And when I get to the z dependence, I'll have n squared nz squared pi squared over L squared. So that Schrodinger equation is based on the summation of momentum squared, px, py, pz. That's a summation. This is a summation of partial derivatives, of second partial derivatives, and the energy formula will be the summation of nx squared, ny squared, and nz squared terms. So it looks like it worked. The wave function here matches the wave function here, and that tells me that this is an eigenstate. It's a quantum state, and that the energy of that quantum state is given by that entire expression. So I need to know the dimensions of that cubic region. I need to know L. Since all the L's are the same, there's just one to work from. And then I need to know the mass of the particle inside. Maybe it's an electron. Maybe it's a proton or a neutron. But I need to know what the mass is. And then I need to know Planck's constant. And I need to know not one quantum number, but I need to know 3 separate quantum numbers. So this is a general pattern or a trend or a feature of quantum mechanics. For each dimension that's being quantized, I'll need a quantum number. And so I'm going to have this quantization taking place in 3 different dimensions. Okay, I switched over to kinetic energy. Did you guys catch me on that? So I pulled out the energy formula. Here is that box with the electron inside. And I got these 3 quantum numbers, nx, ny, and nz, ready to go. I have my h bar squared over pi squared over 2ml. I'm going to do the very same thing I did before. I am going to get rid of the h bars and replace it with h. Now I covered this. I should have moved this over. I covered this up right here. These factors go together. So smush those together as one expression. That is my kinetic energy expression. If I want to use the hc mc squared shortcut, I could use this lower equation right here. So let's see what the pattern of quantum states is. This is kind of new. And we want to be a little bit careful with this. So the lowest quantum state, apparently, would be nx equals 1, ny equals 1, nz equals 1. I put them right here. I thought, come on, nothing's going to be lower than 1, 1, 1, because 0 is not a possibility. So that would be the lowest quantum state. The energy, the kinetic energy of that lowest quantum state is 3 hc squared over 8 mnc squared L squared. So the lowest kinetic energy now is 3 times larger than it was in one dimension. So I drew that on my energy diagram here. So there is that lowest quantum state. And it's unique. There's only one quantum state with the quantum numbers 1, 1, 1. Now, when I move up to the first excited state, I'm actually going to have a set of excited states, because I could have an excited state 1, 1, 2, where there's an excitation in the z direction, or I could have 1, 2, 1 or 2, 1, 1. There's actually 3 ways that we could boost the quantum numbers that would give us a total of 6. And by 6, that's the squared sum together. That's 4 plus 1 is 6. And so there's 3 of those. Now this 6 hc squared over 8mc squared L squared, that's twice the energy of 3. So there's going to be a lowest quantum state. But notice now I have 3 quantum states, and they're at double the energy. Now compare that with the one-dimensional case. In the one-dimensional case, we had the lowest quantum state, and then there was only one more quantum state that was excited. The next excitation, there was only one quantum state of that energy, and it was 4 times as much. And then the next one was 9 times, and the next one was 16. So in the one-dimensional case, we saw that this spacing got larger and larger, and that at every energy level, there was only one quantum state. Now we're finding out that the possibility of having more than one quantum state with the very same energy. And that the spacing, when we move to 3 dimensions, they don't jump as quickly. The spacing between the levels, is actually much smaller. If we move on to the next set, I hope that this is the right one, there's a set of 3 quantum states which have quantum numbers 1, 2, 2, 2, 1, 2, and 2, 2, 1, and they correspond to 9 sort of units of kinetic energy. What would be the one just be above that? Now, there would be a 1, 1, 3, and a 1, 3, 1, and a 3, 1, 1. What would be the numbers on that? If I had 1, 1, 3, that would be 9 plus 1 plus 1. That would be at 11. So there's a set of 3 at 9. There's a set of 3 at 11. And then I tried 2, 2, 2. So 2, 2, 2 would be 4 plus 4 plus 4 would be 12. And that's unique. There's only one way to do 2 plus 2, 2, 2, 2 as an energy state. So there are 3 states at 11, but there's 1 at 12. So that's how this works. We're starting to see more complexity. So we're starting to see that all of these quantum states, there's going to be an unusual pattern to them. What I have to do is take every possible integer combination of 3 integer numbers and then figure out what the states are going to look like. Let's say if we did a 1, 3, 1, 2, 3 would be 1, 4, 9, that would be 14. How many ways could we do 1, 2, 3? And that would be 3 possibilities, and that, I think it's 6 different possible ways we could get that. So we can have 6 states with the same energy. These are called degenerate states. So there's a degeneracy of 3 here, and a degeneracy of 3 here, and a degeneracy of 3 here. With 1, 2, 3, I'm thinking, if I'm thinking correctly right now, there would be a degeneracy of 6. 6 states, all with different combinations of the quantum numbers 1, 2, 3. Now for a photon, what would be the lowest energy photon transitions? And notice you could have electrons transition from any of these set of 3 degenerate states here. One of those would be 1, 1, 2 minus the energy of 1, 1, 1. That would give us 3 units. 6 minus 3 is 3. Okay, so hey, that's how this is going to work. And so we are going to be, for the low end of these energy states, we have to go in and just kind of count all the different possible combinations of these quantum numbers. But if you had a lot of quantum states, you know, millions of quantum states, this becomes kind of tedious. We're going to find out that there's kind of a shortcut method we can use for that. Now, I thought it would be useful too, we're getting close to break time here, so we'll probably take a break here in just a couple minutes. But a good place to stop for this first portion is to go back and look at the quantum states we had defined and look at the probability distributions. So the wave function we came up with was a squared. Now that's a normalization constant. It's going to be related to, it's actually 3 powers of 2 over L square root. But anyway, you could imagine doing a normalization problem with this. It's going to be sine squared in the x, sine squared in the y, sine squared in the z. So that's what the probabilities look like. Now, what do 3-dimensional sine squared functions look like? And they're going to have nodes. So for the state 1, 1, 1, all of these sine functions will have just one bulge in the middle. So that says that I'm going to get a function, x, y, z, with lots of probability bunched together in the middle, but we're going to stay away from the edges. So that kind of looks like an s orbital, if you've taken chemistry and looked at different atomic orbitals. That's kind of like an s orbital, right? Where everything is kind of bunched into the middle region. What would happen if I now jumped up to the 1, 1, 2, 1, 2, 1, 2, 1, 1 states? And here we would have nodes, either in the x direction, the z direction, or the y. In just one of the dimensions, we would divide into 2. So I would have an oblate spheroid here and an oblate, a flattened sphere, top and bottom, or a spheroid. Here I would have, I don't know if you can tell, but that's front and back. So there's a flattened disc, or a flattened sphere, a disc, like a rounded disc in the front and a rounded disc in the back. And then here I would have them side to side. Okay, for those of you who've taken chemistry, what do those look like? And they look like p orbitals, right? I've got a pair of lobes in one direction or the other, or this way. So even though we're using this cubic geometry, we're getting some of the same features that we get from 3-dimensional spheres, which is what the hydrogen atom, which is what atoms, when we come back in chapter 39, will switch over into spherical coordinates. It's something to look forward to, right? And we'll switch over into spherical coordinates and go back and solve. We'll switch the Schrodinger equation into spherical coordinates and come back and solve for hydrogen quantum states. So something that looks kind of like, it's kind of SE, and something that looks a little PE right here. What would happen if we did the state 2, 2, 2, just as an example? And for 2, 2, 2, that would be dividing the region into left and right, top and bottom, front and back. So we'd have 8 separate regions. I would have 8 smaller cubes, and they would all have their own sets of nodes. And so we would have 8 regions, 8 little bulges of probability, a set of 4 at the front and a set of 4 behind, which they kind of look like d orbitals. Okay, and so again, we're starting to see some of the features that we see in chemistry and chemical bonding with these wave functions. So going into 3 dimensions is definitely, I feel like it's worth it. The textbook doesn't do it now, but in chapter 40 they come back and do go into 3 dimensions. So I thought, why not do this now and get it taken care of? And we can think of this as kind of a lead-in for atomic orbitals. So if you guys have questions on any of this stuff, stop by. We'll take a break now. We'll come back and finish up the day.